I want to wrap up the discussion of organic compounds here by talking about structural isomers. So one of the most interesting features of organic molecules is the existence of what we call isomers, which are molecules with the same chemical formulas but different chemical and physical properties. Now there are different types of molecular isomerism. The one I will just discuss briefly here is what we call constitutional or structural isomerism. So for example, here is structures of an alkane with 4 carbons. The formula has to be C4H10, but there are two different ways you can draw the bonding with that same formula. You can draw it as a linear chain, or you can draw it as a branch chain coming off the middle carbon. Now, what's interesting about these two is that even though both formulas are C4H10, they have different chemical properties. The density is different as well as the boiling points. Here's another example of structural isomerism with 5-carbon alkane chain. So there are 3 ways you can actually draw the bonding pattern so that they're different from each other, from a real extended structure like the one shown for pentane, all the way to the very compact structure shown by 2,2-dimethylpropane. Now, when you look at the boiling point, you notice that the most extended structure, which is pentane, has the highest boiling point, and the most compact one has the lowest boiling point. Hopefully this reminds you to the idea of polarizability, which we discussed when we talk about London dispersion forces. If you don't remember this, you can search this channel for a video on intermolecular forces. Remember that the electron density in this type of structures that is extended will be more easily polarized, which means that that will result in the stronger London dispersion force compared to the structure that is more compact.
So let's take a look at an example of drawing structural isomers for a given organic molecule's formula. So we have here 2 different formulas. Actually, I'm going to work on one of them. So it says here to draw the formula C5H10O, and then you should only use one functional group per isomer. So that's a key information. You don't want to mix different functional groups in one. We saw in this previous example that molecules tend to contain a few functional groups, but in this specific example, we just want to do one. And then we also want to rank the isomers once we draw them from highest to lowest boiling point. And so let's take a look at the isomers that we can draw. I drew them here using the line structure. And again, what that means is that each of the point here corresponds to a carbon atom with the corresponding hydrogen attached to it. So that specific carbon on the edge would be a CH3 group like that. And then the one next to it would be a CH2 group, which is attached to this other carbon, right? So just to remind you of how line structure works. So to draw all of these structures, I try to count, make sure that I have 5 carbons, 10 hydrogens, and 1 oxygen, and all of them have that in this case. And what you can quickly see is once you draw all the isomers, I have 7 here that I draw, and if I miss something, you let me know in the comments. But if you look at all these isomers, you notice that 4 of them are aldehydes because they all have this aldehyde functional groups. And then the other 3 are ketones because they have that ketone functional group of carbon double bond oxygen in between 2 carbon chains. So the way you want to think about this is if you're trying to rank them from highest to lowest boiling point, you have to think about intermolecular forces, right, or IMF, and see what kind of intermolecular forces these specific functional groups can have. The aldehydes have a slightly stronger intermolecular forces than the ketones because the aldehydes have these dipole-dipole of carbon oxygen, but it also, the dipole is connected to hydrogen, which is a smaller atom. That aspect of it causes it to be more easily polarized, as you saw in hydrogen bonding, even though these hydrogens here in aldehydes are not connected to an electronegative enough atom, but due to specific properties of hydrogen that make it generate those hydrogen bonds, same thing here, these hydrogens bonded to carbon will also likely be more polar than it is for the ketone example where the carbon is bonded to other carbons. So that makes the aldehydes in general have stronger dipoles, and so we would expect all the aldehydes on average to have higher boiling points compared to the ketones. And then afterwards, we would try to look within each group to try to see if we can predict some kind of a ranking within there. And again, sometimes it's just not possible. Sometimes there's, some trends you can look at. So the other trend that we can think about is that idea of polarizability, which is related to molecular shape. So remember remember that if the shape is more extended, then that means it's easier to polarize, then it will lead to a stronger London dispersion forces. And so if we look at these four aldehydes at the top, this one definitely looks the most extended. And then these ones have a branch, so it's less extended. They both have one branch. And then this one has two branches. And so the way I rank this is I say this most extended one is number one because that would have the strongest LDF within that group. And then these two both are the same. And then this one is the last one. So within the aldehyde, then that's how the ranking of boiling points go. And then when you go to ketones, again, we're looking at the extended versus the less extended one. And the middle one here is the most extended because that's just a long chain of ketone that's linear. And then the other two have some kind of a branching. In this case, the ketone is right in the middle. In this case, the ketone is in the one of the carbons, but then there's a branch right here. So I would say that these two are fairly similar. Maybe one is a little bit higher than the other one, but those two would have the lowest boiling point. So the way I rank these isomers here is as 1, 2, 3, 4, 5, with 1 being the highest boiling point and 5 being the lowest boiling point. So try this out with C5H10O2. You're going to have a lot of isomers in there, but I think the key one is to notice that what functional groups are going to be present first. Like the example that we just did, there's only aldehydes and ketones. Given the formula that we have, we really can't draw anything else. So you'll see that with the C5H10O2, the same thing there. You're only going to be able to do two types of functional groups that are present. And notice that there's 2 oxygens, so that pretty much limits you to specific functional groups that we've discussed.